Polyprotic acids. Polyprotic acids are acids that can contribute more than one proton. In other words, there's more than one hydrogen atom that's part of the compound. The thing that's interesting about polyprotic acids is they always dissociate one hydrogen at a time. The conjugate base of the first dissociation equilibrium becomes the acid in the second step, and the first one is always the strongest. For a typical weak polyprotic acid, like I said, the Ka for the first proton, hydrogen, is greater than the Ka for the second, which is greater than the Ka for the third. So really, we don't really need to worry about the second and the third because they're significantly weaker than that for the first. For typical polyprotic acid and water, only the first dissociation step is important to the pH because the others, although they contribute hydrogen, it's so tiny as compared to the first one that the 5% rule again says it is insignificant. So let's look at the pH of a 1 molar solution of H3PO4. Now, phosphoric acid is a weak acid, but it has 3 protons. And you can see here the Ka for the first hydrogen is 7.5 times 10 to the negative 3, the second is 6.2 times 10 to the negative 8, and the third is 4.8 times 10 to the negative 13. So how would we calculate the pH? Well, we will have to write a reaction, and remember, only one hydrogen is removed. I'm not adding it to water because I know one hydrogen is removed, and that which remains, which is H2PO4 negative, is what remains. So I'm actually only going to look at the first Ka value. This is an ice problem, and this is 1. And you'll start to see these look very familiar. And so what we end up with is, and I'll just come up to the top here, x squared over 1 equals 7.5 times 10 to the negative 3. So essentially we're going to take the square root of 7.5 times 10 to the negative 3. And I actually got 1.06. This slide, which is produced by the textbook company, got 1.08. I tried it several times. I changed the number of significant figures. I don't know how they got 1.08. So I'm going to say it's 1.06. In any case, that's the pH of H3PO4. So let's calculate the equilibrium concentration of PO4 negative 3 in a 1 molar solution of H3PO4. This becomes a little bit more exciting because you will notice that the reaction I wrote before, which was H3PO4, didn't have any PO4 negative 3. It had H2PO4 negative 1. That's after the first hydrogen has been released. After that has been released, we have some H2PO4 negative 1s. And when that releases another hydrogen, we get HPO4 negative 2. We still don't have what this question's asking, which is PO4 negative 3. So we have to remove another hydrogen. HPO4 negative 2 produces the hydrogen, and finally the PO4 negative 3 that was asked for in the question. Now, you can see that when we solve for the hydrogen ion concentration, which I think I had to solve for to get the pH in the first question, I got my hydrogen ion to be 0.0866 molar. That's what I got for that one when I solved for X. That's also going to be the concentration of H2PO4 negative 1, 0.0866, because obviously if it ionizes a certain amount, whatever the concentration of hydrogen is also going to be the concentration of H2PO4 negative 1. The initial concentration of H3PO4 you can see is 1. Alright, so what are we going to do with that? Well, we can see that H2PO4 is the same thing here, 0.0866. But we do not know necessarily the other pieces. What about the hydrogen ions? Well, we can figure out using Ka2, I better do that up here and make sure I have enough room, 6.2 times 10 to the negative 8 equals the concentration of hydrogen times HPO4 negative 2 over H2 PO4. So I know that in this particular question, the concentration of H2PO4 is 0.0866, as is hydrogen, because it's the major contributor of hydrogen ions of these three steps. So even though there's going to be a number here you could use if you wanted to kind of continue on with the x's, it would be so much smaller than 0.0866, it isn't important. So the only hydrogen that's important is really the first one. So when we solve this, of course, this times this over 0.0866, these are 1. So the concentration of HPO4 negative 2 is 6.2 times 10 to the negative 8. Well, that's helpful, but we still haven't found the equilibrium concentration of PO4 negative 3, which is what this question was asking all along. So we're going to do the same thing we did in the last step. We know HPO4 negative 2 is 6.2 times 10 to the negative 8. Hydrogen, as we know, is 0.0866 again. And we're going to then plug it into the Ka3, which is 4.8 times 10 to the negative 13. And products over reactant, 0.0866. And there's our PO4 negative 3. I don't want to run off the screen. And this number is 6.2 times 10 to the negative 8. Now, unlike before, where we just reduced, when we solve for PO4 negative 3, I get exactly what they get, which is 3.6 times 10 to the negative 19 molar. Very, very dilute. And that obviously would be the concentration of the hydrogen ions as well at that time. And you can see it's a very tiny number. So the first Ka value is the important one for us.